Yo, yo, back with Chapter 7 notes. Before we continue, page 3 and 4, I want to recap a little bit what we've been talking about. So remember that this chapter we're dealing with linear regression, and linear regression just means the act of finding an equation of a linear function that best models a scatter plot. So we were given data, we applied it to the 6 actual points, and then we were able to use our calculator to find the equation of the line of best fit. And our calculator also gave us our correlation coefficient, this R value. So we saw we had a moderately strong association. It was positive. We calculated the line of best fit as y hat equals 54 plus 26x, or the predicted total cost is about 54 plus 26 times each pair of jeans that you buy. And then I kind of went backwards a little bit and I explained to you how did the calculator figure out this equation. And what the calculator did is it figured out a way to minimize the residuals. And remember what a residual is it's the actual amount minus the predicted. So here's a nice little picture where we can see like the blue dots above. These are actual points, and even these below are actual points. And we want them as close to our line as possible, all of them. And in that case, we would minimize the residuals. And we can actually figure out what residuals are by just doing the actual values minus predicted and so on. Okay, so you should know that a line of best fit, our linear regression equation, is just a line that minimizes the residuals. One thing I also mentioned we kind of left off on last time was that the point, this linear regression equation, it must go through the point x bar comma y bar. And this is just the average of all your x coordinates and the average of all your y coordinates. And then I even showed you that, like, hey, here's your regular linear regression equation. And if you plug in x bar and y bar, because you know that that for sure is a point on the line, you can get a new equation. But really, these are the same thing. All right, so what we're going to do is continue with that. A couple of these things on this notes packet, I'm not going to lie, I'm kind of going to skip for the sake of time and importance. So let's go ahead and erase that. And then the slope. The slope, we know that from looking at our equation, is b. And there's actually another way to find out what the slope is. I'm not going to get into how we got this equation, but to find out what the slope is, you can take your correlation coefficient r and multiply that by your standard deviation of your y coordinates divided by the standard deviation of your x coordinates. So this equation is also on your formula sheet. So these 3 equations here are all on your formula sheets. Now, why the heck would you ever want to find the slope this way if your calculator gives you the slope, right? Remember when we did regression, the calculator told us that the y-intercept was 54 and the slope was 26. So why the heck would we ever even care about this? Well, there's going to be some questions, guys, where they literally just give you, they don't give you all the statistics. They just give you a few summary things. So for example, let's say this exact same situation, like the number of jeans and the total cost. The question could have said, hey, on average, you buy 7.5 pairs of jeans. And on average, they cost $245.83. And then if they also gave you the standard deviation for each of these, and I'm just going to tell you what they are. We could figure these out using the original data points, but let's just say that the problem gave you this and said, okay, on average you buy 7.5 jeans and their average cost is, $245.83. Given these standard deviations, can we calculate the line of best fit by hand? All right. And this is actually something that many of you have been doing since 8th grade. It's going to look a little familiar. But all this is, guys, is we know that we have this equation, and we're going to try to figure out what is the y-intercept and what is the slope. And we can do that because as of right now, we know two things. We know x bar and y bar. And we can take these and plug them in because we know that this has to be a point on the line that we're trying to find. So I can plug these in and then figure out the remaining two pieces. So before we even plug them in, we can actually figure out what the slope is, b, by using this equation that I just gave you. And like I said, it's not important right now to really understand where this came from. I just want you guys to know that this is definitely given to you on the formula sheet. And yeah, it's just something that you're going to have to use. As you can see here, we do need the correlation coefficient, and we did find that out earlier. I forgot to write it down over here. I'll say R equals 0.74. And this piece of information would also have to be given to you in combination with these other four in order to be able to do these problems. So I can find the slope by plugging in the 0.74 multiplied by the standard deviation of y over the standard deviation of x. All right, calculating this out, we have b equals 25.5. I know I'm good at math, guys, but I didn't do that in my head. Just want to throw that out there. All right, so we have the slope. We're still missing the y-intercept, right? We have b. We're missing a, though. But I can plug three things into this equation right now. I can plug in b, I can plug in x bar, and I can plug in y bar. Because remember that equation I showed you up here? All this means is you're plugging in x bar and y bar. So let's plug this in. Y bar is 245.83 equals, we don't know what a is. Remember, a is our y-intercept. Plus b, our slope, times x bar, which is 7.5. And then this is simple algebra, guys. If we go ahead and solve this, we have a plus 191.25 subtracted to the other side, and we would have a equals 54.55. So we have now our y-intercept, and we have our slope. I can say that now my equation is, and again, if I just rounded here, my y-intercept, let's say, is 55 plus 26x. Make sure you have y hat. Or again, this could have been your predicted cost equals 55 plus 26 times the pairs of genes. Either of those is acceptable. All right, couple little things here. If you've noticed, your calculator not only gives you r equals something, but it also gives you this r squared thing. And all this is, r squared, is you take your correlation coefficient and you multiply it by itself, so r times r, and then you get this r squared value. A couple things with this r squared value is whenever you see it in stats, it's always written as a percent. So r squared should always be written as a percent. And with r squared, guys, literally the only time I've seen it come up in AP stats well, one of two times, is they ask you to take your r squared value and explain it. All right, so like for our scenario where we had, what was our r value? 0.74. If I did 0.74 times 0.74, get 0.55. And so remember, this must be a percent, so it's 55%. What you do with this is there's a sentence that you can make out of this, all right? And for right now, and after teaching this course a few years, I don't think there's much to be learned about this this specific statistic, but it can come up on the AP test, and I just want to give you like pretty much what the formula is if it comes up. All you have to do is like write a sentence, and that sentence is your r squared percent. So blank percent of the, we could say, variance or variability in the y quantity. So whatever it is that the y quantity is, so like I think in our case it was total cost, can be explained by the variance in the x quantity. So I recognize that right now I'm literally giving you like a cookie cutter formula, but believe me guys, I don't think there's much value to be seen from this statistic besides this. So like for this example, what if we know the r squared value, we can say 55% of the variance in the total cost can be explained by the variance in the number of pairs of genes. All right, guys. And then these last regression assumptions and conditions, I mean, we already mentioned this before, just refresher. We need to make sure that we have two quantitative variables. Otherwise, we can't have a scatter plot. We can't have correlation if they're not quantitative. We want linear data, not curved. It wouldn't make sense to run linear regression on something that has a curved pattern. That'd be bad news. Then we'll get to spread should be consistent. And there should be no outliers. Now, I'm mentioning these right now, guys, but assumptions and conditions are something that we need to, as the year goes on, really start talking about more specifically. We can't just run statistical tests and create statistical models on data just because we feel like it. We need to make sure that they meet specific criteria. Otherwise, you're running tests for wrong types of data. So in this case right now, all I really want you to know at this point, like for linear regression, we should have quantitative variables, or we can have a scatter plot, and then like we should have a linear form. Like it shouldn't be curved. All right, these other two are not really important right now. We will come back to this later on in the year. All right, guys, that's it for these notes. Don't submit these just yet because there is, I believe, one more page that will